Hello everyone, welcome to Policy Engine training session. Today, I'm Vahid. Today, with Maria, we are explaining the new features and advancement that we are working on the Policy Engine UK side. Um, okay, the plan for today is first we are explaining the new reports, research reports that we prepared. One is policy engine, taxes in policy engine. The second is benefits in policy engine, and the last one is childcare programs in policy engine. Then Maria will explain the micro impute and micro calibrate packages and dashboard in policy engine. And after that, we are seeing the plans for the next training session and Q&A. Okay. For the reports that we completed over the last few weeks, first I start with the taxes, benefits, and then childcare programs report. So for the benefits, yeah, we wrote a kind of comprehensive analysis on the benefits, UK benefits in Policy Engine and how we model the benefits. So we cover both means tested and non-means tested programs, including childcare programs, for example, and disability benefits. Um, in the report, we actually link each segment to the implementation and the code base, the GitHub that is publicly available, so you can check that. And also, we offer a kind of costs and distributional analysis and the impacts of each benefits that we are model. Um, for example, here we can see that the policy engine estimates for each of these programs, for example, universal credit, housing benefits, tax credit, and pension credit, and so on. And we compare the policy engine estimates with the OBR government estimates. So you can actually see that what is the difference of targeting that we have. And yeah, we are in the implementation. The steps that we covered is that we, for example, implement the eligibility criteria, the calculation methods, and after that, as I said, we have actually a kind of economic impact analysis. For example, what is the distributional and what is the effect on a specific household on the household side. Just for an example, I put it here, the disability living allowance program here. DWP provide that, and it includes two components, self-care and mobility. On the left-hand side, you can see that what is the distributional effect of this program on each decile. So we can see that the higher impacts are for the deciles 1, 2, 3, and we have lower impact on the last deciles. On the right-hand side, you can see that what is the effect of receiving DLA program based on the household employment income. So for lower income, as we have the universal credit, you can see that we have a kind of gap here when we, for example, consider without DLA and with DLA scenarios, and after that we have this effect diminished, and we have a closer gap here. Okay. The second report that I want to talk is that this is the taxes in policy engine. Again, here we model taxes program and components on the UK side in policy engine. Yeah, we both modeling the existing taxes and the UK tax system and also proposed taxes and contributed taxes. For each one, we link the components to the specific implementation in the code base and GitHub, so you can check it and also read the documentation, how we implement that and how we model that. For the taxes, again, we compare the policy engine estimates with the government, mostly from OBR. So you actually be able to compare what is the difference between our estimates and governments, and also see the distributional impact again, for example, uh, poverty impact, inequality impact for each one. The third one is childcare programs. So we actually talked about the childcare programs in PolicyEngine last training session. But here I want to introduce the PolicyEngine program report that we made. In PolicyEngine, we simulate 5 major programs um, for the childcare, including the tax-free childcare and free childcare entitlements, like targeted and universal childcare. Um, Again, for each program, we actually put the links for the implementation in the code and all of the conditions, all of the requirements, and how we handle them, and what is the relationship between them. And for example, if there is a kind of interconnection between these programs, how we handle that. Yeah, and also we use a kind of take-up rates uh, for each of these programs to reach the targets for the spending and caseload statistics from government. Um, Here you can see that what is the difference in our implementation. I mean the targets from the budgetary impacts for each of these programs, and also the difference of the caseloads that we are modeled compared to government. Um, yeah, here just for an example, I put a targeted childcare entitlement. So this entitlement is about free childcare for eligible 2 years old in England, and each eligible uh, child receives up to 570 hours per year. And on the left-hand side, you can see the distributional impact on each constituency uh, in the UK, in the England, because it's not applied for example, Scotland and Wales. On the right-hand side, you can see that what is the effect of different what is the effect of targeted childcare in each scenario, for example, without targeted childcare. So based on the employment income for the household, you can see that on the lower income rates, uh, we have a kind of impact on diminishing the targeted childcare. You can see and check other uh, economic analysis for all of the childcare programs and entitlement within each report and see what happened. For example, if we consider one program or not, what is the economic impact, what is the distributional impact, and also the impact on the household side. So I will hand it over to Maria to talk about the micro-impute and microcalibrate.
Thank you. Hello, everyone. I'm Maria, and I'm just going to walk you through the 2 packages that we have developed in PolicyEngine so that we kind of export the software that we use to prepare our data so that then we can conduct our analysis. Thank you. Right, so let me start with microimpute. Microimpute is a package that essentially takes different imputation methods that are already out there in the world and makes functionality much easier to use around them. And in this process, we provide users with a few advantages. So, for example, a key characteristic of microdata is that it often brings in survey data weights to represent how representative of like the true population a specific record is. And microcompute is able to handle this survey weights by sampling so that the distribution that we use to impute is actually representative of this the true distribution. We also provide different benchmarking and comparison methods because one of the strengths of microcompute is that because it has multiple methods, we can also understand which one is the best one to provide imputation in our survey data. And we also want to make sure that this is flexible so that users can choose when to specify certain things or others. So hyperparameter setting is an option, and also we make tuning hyperparameters fully automated so that with a simple Boolean turning it on, we can perform all of the tuning to a specific data set. We also have quantile-based evaluation to make sure that when we are imputing, we capture the accuracy of methods across all of the distribution and not just in the mean or the median of it. And so what this quantile loss metric that we use does is it penalizes over prediction in lower quantiles and under prediction in higher quantiles so that methods can accurately predict how values will change across the whole distribution. And finally, one of the most important things is that we have auto-imputation, which means that we built a full pipeline that allows the user to, with a single call to a function, go through the whole process of setting up the data set, running imputation with multiple methods for transferring the variables that they're interested in, then compare all of those methods, identify which one was actually the one that performed the best, and then choose that one to perform the final imputation and return a fully imputed data set that then can be ready for analysis. Thank you. So just to give you an example of how this would work, I have here a case from US microdata. The US analysis that we perform relies on two main data sets. One of them is the Survey of Consumer Finances, which is really useful for us because it has a lot of information about the demographic characteristics of households in the US, as well as detailed income records, etc. So it's easy for us to understand how different families might have income depending on their characteristics. And at the same time, we also have the current population survey that provides a lot of information about like employment status, labor force, etc. Because it also has demographic characteristics, there's some overlap with the survey of consumer finances, but it is much less detailed in the information that it provides about families' assets, etc. These variables specifically are super important to estimating wealth, which is something that we would love to do for our analysis, but we cannot do it if we are only relying on one of the two data sets. And so to bridge this gap and be able to kind of bring all of the information together in a single unified data set, and then we can use for analysis, we use microimpute. So what we do is we impute wealth from the SCF to the CPS, and then integrate it all so that we can use that data. The right plot shows the two distributions that each of these data sets has. The SCF distribution is the distribution that the data records already had in their survey design, and the CPS is imputed. So originally we had no data at all about this, but then after we use our predictors to impute, we managed to achieve this very similar looking distribution to the SCF for each household in the CPS record dataset. Additionally, because microcompute supports benchmarking and method comparison, we are able to also contribute to the research that moves imputation methodologies forward. And so one thing that we worked on is writing a paper that would evaluate whether machine learning can actually produce better imputation than other more traditional methods like statistical matching or simple regression. And yeah, we found that our analysis actually demonstrated that quantile random forests, which is the machine learning model, outperformed all of the other methods when imputing wealth from the SCF to the CPS. So that's what you're seeing in the plot on the right. We tried 4 different methods, QRF, which is this quantile random forest machine learning model, OLS, which is like simple regression, statistical matching, and QuantRec, which is a less developed machine learning model. And you can see that on average, QRF performs better because the lowest line is the one representing QRF. But also at the same time, we can see how QRF does throughout the distribution because we have all of the quantiles, well, 20 quantiles modeled at the bottom, and QRF outperforms in every single one of them except over the 85th quantile, which is really good for what we're looking for. And now I'm going to talk a little bit about microcalibrate, which is the package that we use to calibrate data once we've already imputed all of the variables that we needed. Calibration essentially just means taking the survey weights that I was talking about that tells us how representative a household is of the true data and changing them so that we actually achieve the specific targets that we know to be true about the real world. So for example, if we know that employment income has to have a specific total in the US, we can optimize those targets so that the total is achieved. We provide some functionality in our microcalibrate package to make this optimization very simple. We use a gradient descent machine learning algorithm, and to make it very easy to use, we just have a calibration class that the user can call. This class is also very flexible, so you can set up different parameters to choose whether you would like to, for example, subsample or drop records that are not very explanatory to the calibration process, or whether you would like to keep all of your data in it. And finally, we're really happy to show a dashboard that we have built to observe how this calibration is actually doing in the background. So every time we calibrate, we save a log of how the performance changed over time and all of the epochs that we trained for. And we have a dashboard, like you can see on the right, the opening page, that actually shows how the data changes over time and whether calibration improved throughout epochs, as well as providing very detailed visualizations for exploring each of the targets.
Maria, do you want to? I can stop sharing and you can share your screen if you want.
Yes, that would be perfect.
Uh,
Okay, let me give you a quick demo of how that would look like. Can you see my screen?
yes.
Perfect. Okay, so this is the opening page of the dashboard. It allows you to log your data in different ways. You could drop your file from your saved CSV. If you have a public URL that has public access to the data, you can also use that. And importantly, one that we love is GitHub access. You can point this dashboard to a specific GitHub repo, branch, and commit to load your data set. We also have sample data if you would like to observe it, but I'm going to show you how the GitHub works. So let's go to UK data. Okay, so now that I loaded my file, I can see the calibration summary here. First, we can see how, well, this says that we achieved excellent quality, but that's only because we have two targets. So it's a very easy test that we put this through. But yeah, we have two targets that we calibrated for. And because we run this for 120 epochs, our model was able to optimize our weights very easily. One of the features that we provide is a summary of which individual targets improved or got worse throughout the process. We can see that the two targets that we calibrated got much better throughout the process. And then we can also observe how the total loss and the total relative error changed over time. So for example, we want to look at the error changes here, or we can also toggle this and prioritize loss instead. And then we can dive deeper and do this for each individual target that we like. So this one is for the income for people aged between 20 and 30. We can also switch it for income between 40 and 50. This is synthetic data, by the way. So these are not true values. And then we could see how the loss, the error changed over time and how our target was achieved throughout our epochs. And then finally, we can, well, not finally, but almost finally, we can, when we have a lot of targets, also see how they compare to each other and they compare to their estimates. So right now we can see that they achieved the exact same value because the calibration worked really well. But if we went to the epoch 0, we would be able to see that actually our estimate was somewhat far away from our target values. This lets us play around with the whole process to see where things went wrong or where they might have improved, and then iterate on our process through it. And finally, we can also have our detailed results here that lets us both search for target names. So we can just do page 20, and that will toggle whatever we're interested in. But also we can sort our data through the relative absolute error. So if we had really bad performing targets here, we would also be able to put them first. And this is for a single CSV file, but I also would like to show you what happens if we do this for a comparison of two different commits. So I can click this to compare two calibration runs, and I'm going to choose a different calibration that we did deliberately wrong so that we would be able to observe that it didn't work. Right now we just have our data loading because there's a lot of epochs that were run for, so this takes some time. And then we get here. So as we can see, the second one actually did much worse because we essentially removed all of the employment income data that was in it. So the targets were impossible to achieve. So we can see that 2,266 targets did better in this second run, but most of them, 8,071% of them, actually did worse. Then we can see a very detailed summary of how that went, a breakdown of which targets were doing better or worse and how many worsened over time, as well as a comparison of overlap. So there might be instances in which some targets are in one of the CSVs, but not in the other. So we can also know which targets are available for comparison. Similarly to when we were looking at a single CSV, we can still see how loss and error changed over time across epochs. And we have a correlation analysis to understand how similar the two runs were. This statistical interpretation helps us understand a little bit better what we're looking at. So for example, here we have a moderate similarity because we removed employment income. We know that the second run wasn't expected to be very similar to the first one. So we only have a slope of 2.43. Look here. And the average errors got much worse. In the first one, we had an average error of 4.86%, and then in the second one of 31%. So that's much higher, which means that overall, the first data set was performing better. We can also dive into the specific targets. For example, here we calibrated for all of the UK areas, so I can search, well, I don't know, say I would like to look at this one, or I could look for the employment income of one of them. It takes a little to load because there's a lot of data in it. Okay, here we go. We can see that the first one did much better than the second one because we removed the data altogether. And this is the dashboard that I wanted to show you. Essentially, we can also look at the bar charts. So if I go employment income, yeah, ooh, without typos, that'd be better. Okay, we can see that, especially, let me see if I can put epoxy row. At the beginning, without calibration, our estimates would have been really, really far off our targets in either of the runs. But then, let's see if we can. Okay, after some calibration, our first run, which was the one that we were using employment income data in, actually achieved our target much closely, while the second one obviously couldn't because we removed all of the data. So this helps not only to just compare and play around with a couple of visualizations, but also diagnose what might have gone wrong and then iterate over the targets that we want to build. And finally, you can always share your dashboard with your friends or colleagues if you need to collaborate in that calibration process. I will stop.
Yeah, thanks, Maria. Okay, I can share my
My
screen again if you.
perfect. Let me see here. There we go.
Sure. Um, do
Perfect.
you
Actually,
have my
those
screen?
are just snapshots of,
Okay.
yeah, we can see your screen. Those are just snapshots of the, yeah, dashboard I just showed.
Okay, perfect. Yeah, thanks, Maria, for the explanation. Um, yeah, the plan for the next training session is we want to present the structure reform and non-parametric simulation, and also we'll deep dive to public services imputation and how we model them. So save the date for the next training session. And if you have any question right now, feel free to ask. Thank you.